Today's subject is Taylor polynomials and Taylor series. First thing to realize is that at least with Taylor series, it's nothing too different from what we did in chapter 9 with power series. In fact, Taylor series are power series. They're a special kind of power series. As far as Taylor polynomials go, that's just trying to build up toward Taylor series. It's good to start by reviewing something we know from Calc 1. In Calc 1, we had the idea of the local linearization of a function near a point. Local linearization of a function f near some value of x, often called x equals a. What is the local linearization of f near x equals a? It is a linear function, call it L of x, whose graph is the tangent line to the graph of f at x equals a. If the tangent line exists, meaning if the derivative f prime of a exists. L of x equals f of a plus f prime of a times x minus a. The graph of f is a curve. Maybe it looks like this. Let's say a is right here. The second coordinate of that point would be f of a. And the slope of the tangent line would be f prime of a. There's the tangent line. Tangent line. The slope of it equals f prime of a. The blue graph is the graph of the function y equals f of x. What I claim is this, maybe it's hard to tell the color there, this green graph is the tangent line itself. It's the graph of L of x. Y equals L of x. Why? Why is that the graph of L of x? First of all, it's got the right value when x equals a. L of a, if you use this formula, is f of a plus f prime of a times replace x with a minus a. That's a 0. This whole thing is 0. This simplifies to f of a. Think of a as a fixed number and x as the variable. At this fixed number a, the value of L there at that point is the same as the value of f. They go through the same point right there. They also have the same slope. As a function of x, where a is constant here, that's a linear function of x. Its derivative is the coefficient of the x term. Its derivative is f prime of a. In fact, that's true no matter what x is. L prime of x is a constant function, f prime of a. So also L prime of a equals f prime of a. The graph of L is a straight line. It's got a constant slope. Okay, so this function L of x matches the function f at x equals a in two ways. They match function values and they match slopes. And what that means is it's probably a good approximation to f near x equals a. We will do an example. But before we do an example, let's generalize this. This is a Calc 1 idea, local linearization using the derivative. Maybe now it would be a good idea to generalize this to a local, what should I call it? Quadrization with a quadratic function instead of a linear function. That's probably not a word, but I'll make up a word here on the spot. Local quadrization. Technically, a better phrase would be quadratic approximation. The local linearization was a linear approximation. The local quadrization would be a quadratic approximation. Probably not a word. Q of x. Q for quadratic. What should we do? Well, maybe initially you write it as a typical kind of quadratic, ax squared plus bx plus c, although maybe I should use capital letters because that a is not the same as the other a. Let's do that. Let's use capital letters. Capital ax squared plus capital bx plus capital c. To keep things simple, let's let little a be 0. When you do local linearizations, and what we're doing today, the Taylor polynomials and Taylor series, 90% of the time, a is 0. Maybe about 10% of the time, a is not 0. Let's use a equals 0. What I'd like to do is I'd like to match up the value of q at a equals 0 with the value of f there, the value of the derivative of q at a equals 0 with the value of the derivative of f, and the value of the second derivative of q at 0 with the value of the second derivative of f at 0. To do that, I guess I better differentiate q. Q prime would be 2ax plus b, a linear function. When you differentiate a quadratic, you get a linear. Q double prime of x is going to be a constant function, 2a. The second derivative of a quadratic is a constant. Yeah, now plug in a equals 0 into all three functions. What happens? In each case, everything but the constant term goes away. Replace x with 0. Q of 0 is c. Q prime of 0 is b. And q double prime of 0 is 2 times a. Remember our purpose. We've got some function f. We're trying to use this quadratic to approximate f near a, which in this case, again, is little a is 0. So it should make sense that you'd want to set these equal to the corresponding derivative values of f, or function values at 0, f of 0, f prime of 0, and f double prime of 0, and solve for a, b, and c. Fortunately, this is a very simple system of equations to solve. There's nothing much to do. C equals f of 0, b equals f prime of 0, and a equals f double prime of 0 divided by 2. It's only in that last one that you've got to do a tiny bit of work. So it looks like that's what we should do. Now, I could have picked a general a, something non-zero, and done something similar. Although if I did, the trick is to make it still work out simpler. Instead of having powers of x, you'd want powers of x minus a, little a. That would be the trick to make your calculation simpler. If you do that, what you're going to get for your general quadratic approximation, your general local quadrization, is q of x equals f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus little a squared. The f of a, that was the c on the previous page. That was f of 0. Compare here. C was f of 0. The b was f prime of 0. That's the f prime of a. Little a was 0 in the example up here. The c here in the example was f double prime of 0 divided by 2. That generalizes to f double prime of little a divided by 2. But again, to make the solving for capital A, B, and C work nicely in a general case, you'd want powers not of x itself, but x minus little a. That's why we have an x minus little a there and an x minus little a squared there. That would be the local quadrization. Could there be a local cubrization? Uh-huh. Oh, such fun with words. C of x. Again, probably quadrization and cubrization are not real words. I made them up on the spot today. It continues to look similar. What would happen, though, with the cube term, the term involving x minus a quantity cubed? Maybe leave it as an exercise to show that you get f triple prime of 0 divided by 6 of all things times x minus a quantity cubed. I'm claiming that's what you would get. You're believing me because we don't have time to verify. Or do we? Oh, okay. Let's do a real quick sort of verification. If I was using little a equals 0 and using a general cubic like this, probably the most mysterious is why is this one involve f triple prime of 0 divided by 6? Let's see if we can at least get an idea about why that's true. Take the derivative. This is what you'd get. Take the second derivative. Get 6ax. There's a 6 plus 2b. Is that 6 an accident? No, f triple prime of x is just a 6a. And that 6 is what's going to lead to the 6 there. 6a would have to equal f triple prime of 0. And you divide by 6 to solve for capital A. And I realized I made a typo here. In general, this is an A here. Likewise, we could do a local quadrization, quartic, fourth degree. We could do a local quintization. Would you say quintization or pentization? Both mean 5. Either one's probably okay. Then a local hextization, 6th degree. Local septization, 7th degree. Local octization, 8th degree. And we could keep going forever and ever, finding higher and higher degree polynomials. They're all examples of what are called Taylor polynomials. The nth degree Taylor polynomial of a function f centered at some number x equals a, written with subscript notation as p sub n of x, is f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus a squared plus f triple prime of a divided by 6 times x minus a cubed plus, let's keep going, f quadruple prime of a over what does it turn out to be? I'm just going to tell you the answer, 24. X minus a to the 4th plus f quintuple prime of a, 5 primes of a divided by 120 of all things times x minus a to the 5th, etc. And if it's nth degree, the last term involves x minus a to the nth power. The coefficient in front involves the nth derivative of f, evaluated a divided by something. What should I write for the nth derivative? Should I put a bunch of primes, then maybe some dots and another prime? I could. That's hard to typeset on a computer. It's more conventional to do this, to put an n in parentheses, evaluated at a. This does not mean not nth power of f. It's not that. This is the nth derivative of f at x equals a. It is standard notation. To try to emphasize it's not a power, that's why the parentheses are around the n. And it's also a function. It's in the section about Taylor series. It's an nth derivative. But n could be humongous. Million, billion, Googleplex, blah, blah, blah. Okay? This could be a humongous polynomial that to write it all goes past the edge of the universe. We don't want to do such examples, but theoretically it's doable, or maybe it's better to say thinkable to do such a thing. But what do we divide by? I hope you kind of see a pattern here. This 2, 6, 24, 120, you've seen this pattern before. That's 2 factorial, 2. No, say factorial. 2 factorial, 3 factorial, 4 factorial, 5 factorial, and in general, it's an n factorial, all times x minus a to the nth power. But wait a minute, is this pattern really holding for the first 2 terms? Yes, it is, because 1 factorial is 1, and 0 factorial by definition is also 1. We already knew that. Why is 0 factorial 1? Here's another reason. So the formula works out nicely. There's lots of reasons 0 factorial is defined to be 1. Pretty much all of them is because it makes formulas work out nicely. And so we could write the general pattern for this in summation notation. Summation, k goes from 0 to n of the kth derivative of f at a divided by k factorial times x minus a to the k power. Including the case where k is 0, you're dividing by 0 factorial, which is 1. You're not dividing by 0. Also, the 0th derivative of a function is the function itself. Why? Because we say so. Convention, definition, it makes formulas work out nice. The 0th derivative of a function is the function itself. Nth degree Taylor polynomial. All right, would we want to do this? Let's do an example. Let's start with f of x equals 1 over 1 minus x. This expression should look vaguely familiar. But let's go ahead and use the formula. Let's write this as 1 minus x to the negative 1 power, so that taking derivatives is pretty quick. I can avoid the quotient rule. The first derivative is bring down the negative 1 minus x to the negative 2, but then don't forget the chain rule. Multiply by another negative 1, because that's the derivative of 1 minus x, the inside function. The negative signs cancel, and you're left with 1 minus x to the negative 2. Second derivative. Differentiate this. Bring down the negative 2, 1 minus x to the negative 3. Don't forget to multiply by negative 1. 2 times 1 minus x to the negative 3. Third derivative. Bring down the negative 3, get negative 6, 1 minus x to the negative 4 times negative 1. Positive 6, 1 minus x to the negative 4. We're seeing factorials again, aren't we? Fourth derivative. Negative 24, 1 minus x to the negative 5 times negative 1. It's positive 24, 1 minus x to the negative 5. That's the fourth derivative. There's supposed to be 4 primes there. We could keep going. What should we use for a? Technically, anything except 1 is okay. But 90% of the time, we use a equals 0. A equals 0, so let's do that. F of 0 That's f of a is 1 minus 0 to the negative 1 is 1 to the negative 1 is 1. F prime of 0 is 1 to the negative 2 is 1. F double prime of 0 is 2 times 1 to the negative 3 is 2. F triple prime of 0 is 6 times 1 to the negative 4 is 6. We're getting factorial values. This one's 24 times 1 to the negative 5 is 24. And yeah, I could say this is 0 factorial if I wanted to. This is 1 factorial. This is 2 factorial. This is 3 factorial. This is 4 factorial. It looks like the nth derivative or the kth derivative, say, at 0 is k factorial. What does this mean as far as the Taylor polynomial goes? P sub n of x, I'll write the summation form of it. Summation k goes from 0 to n. The kth derivative at 0 divided by k factorial times x minus 0 to the k. I'm using a equals 0. Simplifies to what? We have a k factorial divided by k factorial. They cancel. You're left with the summation of just some plain old x to the k powers, which if you write it out is, when k is 0, it's x to the 0, which is 1 by definition, then x to the first, then x squared, then x cubed. Yeah, maybe you guessed this answer ahead of time. The function was 1 over 1 minus x. It's related to geometric series. That's a geometric series, a finite geometric series. That's the nth degree Taylor polynomial. Let's see how well it approximates the function with technology here. So f of x is 1 over 1 minus x. Let's plot the function along with, say, first of all, let's start with just 1 plus x. And let's make the original function be blue and the approximation be red. There we have it. The blue graph is 1 over 1 minus x. Notice it's got a vertical asymptote at x equals 1, right? 1 over 1 minus x definitely has a vertical asymptote at x equals 1. The red graph matches the value at x equals 0. F of 0 is 1. And the derivative at x equals 0, f prime of 0 is also 1. Does pretty well near x equals 0. If I zoom in, say between negative 0.1 and positive 0.1, they're pretty close together. If I up the degree to a quadratic, then the red graph will no longer be a straight line, but instead will be a parabola. The red graph is a parabola. Approximates the blue graph very well near x equals 0. Now they're really, really close together. Let's up it to, how about 7th degree? Plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th plus x to the 7th. Now the red graph approximating the blue graph looks really close over from about negative 0.9 to positive 0.6 or 0.7 or so. They're pretty close together. It's a better and better approximation to the entire function over a bigger interval. Actually, we can confirm this with series. Out to any degree that I want. So this syntax, series with a capital S, the function name, comma, x comma 0 to 100. The x emphasizes the variable as x. The 0 emphasizes the a is 0. And the 100 is going to be the highest degree term that we'll see. There we have it, out to x to the 100th. We also see a big O of x to the 101, meaning there are more terms that have degree 101 or higher. They, in fact, all have a coefficient of 1. We know what they are. The infinite series equals the function. Could I plot this entire thing? I tried it for the first time in the last class. And yes, you can. You can copy and paste this whole thing. Not the big O, though. Don't include the big O. Oh, I'm trying not to highlight it. There we go. Copy and paste the whole thing in here. And it does graph it. It picks the window for you in the vertical direction to include up to 10 to the 12th almost here. It does seem to be indicating that it's a really good approximation when x is close to 0. If we zoom in the vertical direction to a plot range, oh, say between -10 and 10, then we see that the graph is really good between -1 and 1, but pretty bad otherwise. The red graph is a good approximation to the blue graph between -1 and 1, but pretty bad otherwise. That should make sense if you think about it. The infinite version of this, which you could call P sub infinity of x, the infinite version of this, infinite series, it's an infinite sum. It would be a geometric series, an infinite geometric series with plus ... dots going on forever. This is geometric with leading term A equal to 1, but this A is different than the other A. So far today, the little a has represented where the series is centered, having terms that have powers of x minus a. But here, this a is the a for a geometric series, the leading term, 1 in this case, and the common ratio r equal to x. It converges to a over 1 minus x if the absolute value of x is less than 1, and always remind yourself that means x itself is between -1 and +1. And so that when a is 1 and, well, okay, I should have written an r. Okay. Replace that x with an r. X does equal r here, but I should have initially written an r. That does equal 1 over 1 minus x, which is the original function, f of x. So the infinite sum, the series, equals the function. The Taylor series, not Taylor polynomial, Taylor series, infinite polynomial, so to speak, infinite degree, equals the function on the interval of convergence. R is between -1 and 1, but again, because R equals x, that also means x is between -1 and 1. R equals x here. Just notation. Don't worry about it. The infinite sum gives you equality. It's not just an approximation. It's exactly equal. Though, with a caveat, nobody is literally adding up infinitely many things. We're only pretending to, right? But we are pretending to in a rigorous way, using partial sums and limits of partial sums, limits of sequences ultimately, which can be made rigorous, completely rigorous, no doubt about it. This pretending can be made rigorous. It also turns out to be useful. So we do the pretending because of those things. It's also beautiful. So we like it that way too. In general, the Taylor series for f centered at x equals a, call it p sub infinity of x, is an infinite sum, k goes from 0 to infinity, of the kth derivative of f at a divided by k factorial times x minus little a to the kth power. And if you write that out, since 0 factorial is 1, you get f of a for the first term. Since 1 factorial is also 1, you get f prime of a times x minus a for the second term. 2 factorial is 2, so I could write the 2 factorial there as a 2, but I will leave it as a 2 factorial. Then f triple prime of a divided by 3 factorial x minus a cubed, etc. forever and ever. It's a Taylor series for a function centered at some number called a. It is also a power series. That's a power series. That's an infinite sum of powers of x minus a. It's got an interval of convergence. It's got a radius of convergence that could be figured out with the ratio test, and we will. But it's a special kind of power series. It's related to some function f. And we hope that it equals f when you do the infinite sum. It's an approximation to f near x equals a when it's a truncated finite Taylor polynomial. But we hope the infinite sum equals f. Is that true? Is our hope fulfilled? Usually. Although it might be on just some interval that could be small, like -1 to 1. But not always, actually. There are some weird examples where the Taylor polynomial, the Taylor series that goes out forever, does not equal the function, well, except at one point, x equals a. You have to think pretty hard to come up with such an example, though. I will show you an example of that on Friday, as well as doing some other fun things on Friday before your review for the exam, including like talk more about the Riemann hypothesis and make some really cool graphs. All right, Taylor, that's the Taylor series. Let's do another example. How about f of x equals 1 over 1 plus x? Actually, to figure out the Taylor series for this centered at 0, there's a quicker way to do it than taking derivatives. Let me show you that quick way to do it. Think of it as 1 over 1 minus negative x, and think of that then as the sum of a geometric series with a equal to 1 and common ratio equal to x, negative x, excuse me. And there you have it. There is the answer without much work. But let's confirm that it really does work with the formula as well, involving derivatives. This is the same as 1 plus x to the -1. Its derivative will be -1 plus x to the -2, and I do not get an extra factor of -1 this time, because the derivative of 1 plus x is +1, not -1. So the negative sign there does not go away. F double prime comes back to a +2, 1 plus x to the -3, because -1 times -2 is +2. F triple prime of x goes back to a -6, 1 plus x to the -4. F quadruple prime of x goes back to a +24, 1 plus x to the -5, etc. F of 0 is 1 to the -1 is 1. F prime of 0 is -1 to the -2, which is -1. By the way, order of operations here, if it's not clear, is you do 1 to the -2 power first, and then use the negative sign in front of that. So the answer is -1, not +1. Here, f double prime of 0 is +2. F triple prime of 0 is -6. F quadruple prime of 0 is +24, etc. Now plug into the formula. P infinity of x is f of 0 is 1. plus f prime of 0, which is -1, divided by 1 factorial, which I won't write, times x minus 0, which is just x, plus 2 over 2 factorial, x minus 0 squared, plus -6 over 3 factorial, x minus 0 cubed. I'm just taking these numbers that are up here and putting them in there. That wasn't clear. Plus positive 24 over 4 factorial, x minus 0 to the 4th, etc., plus dot, dot, dots. And we get complete cancellations. These are all either 1 or -1. So it does simplify to the same thing. 1 minus x plus x squared minus x cubed plus x to the 4th, etc. Same thing we got, realizing we could also use the geometric series formula up here. And the convergence, once again, is the convergence if the absolute value of the common ratio is less than 1. Common ratio is -x here. Absolute value of -x is the same as the absolute value of x. So this convergence is between -1 and 1. The interval of convergence is that interval. It's an open interval centered on 0. Does not include the endpoints. Radius of 1. What would happen if we tried using the ratio test here to confirm the radius of convergence and the interval of convergence? What would happen? The p infinity again here is 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th, etc. With summation notation, I could write that as summation k goes from 0 to infinity. Be a little careful here. You could write it as -1 to the k x to the k. Double check it in your mind. -1 to the 0 power is +1 times x to the 0 is also +1. By the way, when we use that, we're using the convention that simplifies to 1, even though 0 to the 0 power is undefined. Don't worry about it though. When k is 1, we get -1 to the first power, which is -1 times x to the first. It matches this one, etc. This works. We could take this to be the an or the ak in this case, our general term, and we could look at the ratio that we always look at with the ratio test. We used n before, I'm using k now. And what'll happen here? Well, for one thing, the -1s won't matter because I'm taking absolute values. I do need to keep the absolute value sign around the x, because x could be positive or negative. The power can be brought out. But then these things cancel. This simplifies to the absolute value of x, which does not depend on k. If x is fixed, this is a constant. It approaches itself as k goes to infinity. And what does the ratio test say? It says if the limit of this thing is less than 1, then for sure the series right there converges. If the limit is bigger than 1, it diverges. If it equals 1, the ratio test gives you no information. When is this less than 1? Exactly when it's less than 1. This is equivalent to x being between -1 and +1. That is seemingly at least the radius of convergence. Now, again, the ratio test gives you no information if this limit equals 1. And technically, the limit equals 1 when x is 1 or -1, in fact. So the ratio test gives us no information, but we know, once again, since the series was geometric, that it does not converge at the endpoints. And the interval of convergence really is an open interval centered at 0, not including the endpoints with a radius of 1, just like I said before. However, I'm about to do another example where the interval of convergence does include an endpoint. In fact, one endpoint, but not the other one. Amazing. Proving that it's the interval of convergence is not a difficult proof for the interval itself, but to show it converges to the function f is beyond the scope of what we're doing right now. The example is f of x equals ln of 1 plus x. Why do ln of 1 plus x instead of ln of x? Mostly so that we can continue using a equals 0 and also relate it to the previous example. Yes, we could do ln of x itself, but we could not do that about 0 because ln of x has got a vertical asymptote of 0. So we'd have to use some non-zero a, like a equals 1 perhaps. So to keep it at a equals 0, I'm going to do ln of 1 plus x. But also it relates it to the previous example because the derivative of this is the function from the previous example. I guess the answers must be kind of related as well. Right? Did you catch what I just said there? F of x is ln of 1 plus x in this new example. Its derivative is 1 over 1 plus x, whose Taylor series we just found a few minutes ago. It was geometric. We did it quickly in about 10 seconds. And then we also took the derivatives and confirmed the answer. And we also used the ratio test to figure out, reconfirm the interval of convergence. For the interval of convergence in this case, we'd have to use the ratio test actually, because ln of 1 plus x is not the sum of a geometric series. So evidently the answer, whatever it is, can't be a geometric series, but it's got to be somehow related to a geometric series in seemingly a mysterious way right now. Let's keep going. Let's take derivatives. The second derivative of this example is the same as the first derivative of the last example. The third derivative of this example is the same as the second derivative of the last example. The fourth derivative of this example is the same as the third derivative of the last example. Let's go one more. The fifth derivative of this example is the same as the fourth derivative of the previous example. F of 0 is ln of 1 is 0. That's a little different. The constant term is 0. F prime of 0 here is 1 to the negative 1, which is 1. Same as the f of 0 from the previous example. F double prime of 0 is going to be negative 1 to the negative 2. And again, order of operations is to do the negative 2 power first. So this is really negative 1. F triple prime of 0 is the same as what f double prime of 0 was in the previous example. Yep, that kind of pattern continues. So evidently it's like the coefficients 1, negative 1, 2, negative 6, positive 24, negative 120 would be the next one. They're like shifted. The power of x that they go with is different. The Taylor series, P infinity of x, the constant term is 0. I'll write it down for emphasis. 0 plus the derivative at 0, 1, times x minus 0. I'll write it as x minus 0, but of course it simplifies to x. Minus, careful, the next term is x minus 0 squared, so it does involve dividing by 2 factorial. Negative 1 is f double prime of 0. So we get a minus 1 over 2 factorial x minus 0 squared. With the last example, we got 2 factorial divided by 2 factorial. 2 over 2 is 1. This one does not simplify to 1. Then we get 2 over 3 factorial, the 2 coming from this right here, times x minus 0 cubed. Let's write down, let's go ahead and write down 2 more examples. Minus 6 over 4 factorial, x minus 0 to the 4th, plus 24 over 5 factorial, x minus 0 to the 5th, etc. Simplify. X minus 1/2 x squared plus 3 factorial 6. 2 6 is 1/3 x cubed. 4 factorial is 24. 6 over 24 is 1/4. 5 factorial is 120. 24 over 120 is 1/5, etc. This is not a geometric series. It's a Taylor series. It's a power series. It's a Taylor series for this function, ln of 1 plus x, centered at little a equals 0. It's also an infinite series of powers of x. It is a power series. It's got an interval of convergence and a radius of convergence. What is the interval of convergence? You might think it's x between -1 and 1, and that's almost right, but not quite. It does not include -1, but it does include +1. Why? Because if we plugged in x equals +1, what would we get? We would get the alternating harmonic series. And we know the alternating harmonic series converges. The harmonic series diverges. Remember that for the rest of your life. The alternating harmonic series converges. You should probably remember that for the rest of your life. This converges. If you plugged in -1, you'd get the opposite of the harmonic series. You'd get -1 minus 1/2 minus 1/3 minus 1/4 minus 1/5. It would diverge when x is -1. Diverges if x is -1 because it's the opposite of the harmonic series in that case. So this series, the interval of convergence, includes the right endpoint 1, but not the left endpoint -1. It's a half open, half closed interval. It's a clopen interval, if you will, if you like. Include the right endpoint, but not the left. What was it the series for, though? It was the Taylor series for ln of 1 plus x. Does it equal ln of 1 plus x? See if Mathematica indicates yes or no. First, let's double check it with series. Ln, of course, as always, is log. Looks good, doesn't it? Signs are alternating, plus, minus, plus, minus, plus, minus. Coefficients are 1, -1/2, plus 1/3, minus 1/4, plus 1/5, minus 1/6, etc. And it does go on forever. Let's try plotting it. Along with, well, copy and paste the right series here. Plot this crazy thing along with not the other function f of x, but ln of 1 plus x. The blue graph is ln of 1 plus x. The red graph is this 100th degree approximation. That is a truncated sum. It does not go on forever. There's the highest degree. So these are not exactly equal, but they're so close together, it helps you believe the infinite series equals the function. And it does for this interval of convergence. Proving that's not easy, though. especially proving that it equals ln of 2 when x is 1. Which you might remember, that's what the alternating harmonic series converged to, is ln of 2. That's because when you plug in x equals 1 here, you get ln of 2. But proving that rigorously is pretty hard, beyond the scope of this course. Let's do another example. How about f of x equals arctangent of x? Also known as inverse tangent of x. Oh, really? Seriously? Take derivatives. There's the first derivative. Maybe write it like this so that after this point we might be able to avoid the quotient rule. What's the second derivative? Don't forget the chain rule and get this. What's the third derivative? Oh, I can tell now this is not going to be so pleasant. Because now I can't avoid the product rule. I've got a left function and a right function. I have to use the product rule. Left d right plus right d left. Left d right plus right d left is going to be this, along with another times 2x. Oh, I don't think I want to do any more by hand. We'll have Mathematica do it. A is 0, plug in 0. You know, all these examples today, all we've had time for is a equals 0. I'm going to assign at least one problem on the assignment where a is not 0. You can do all this stuff even when a is not 0, as long as the function and all its derivatives are defined at that value of a. You can still do it. And it's still sometimes useful. Inverse tangent of 0, I hope you remember, is 0. It is. F prime of 0 is 1. F double prime of 0 is back to 0. F triple prime of 0 is not 0 because the first term does not become 0 when x is 0. The first term there, that one, is -2 when x is 0. Right, you get a 1 to the -2, which is 1. Put a negative sign in front of it, get -1 times 2 is -2, etc. So it looks like P infinity of x starts out 0, as inverse tangent of 0 is 0, plus 1 times x plus 0 over 2 factorial times x squared minus 2 over 3 factorial x cubed, etc. X minus 1/3 x cubed. What is the next term? If memory serves me right, and memory goes back to an hour and 20 minutes ago, it's 1/5 x to the 5th, right? The previous section. The next one turns out to be minus 1/7 x to the 7th, etc. And this turns out to equal the arctangent function on the interval of convergence here. That ends up looking like this again. Seems like all these intervals of convergence is between -1 and 1. That just is a coincidence with the examples that I'm picking. You definitely can get other intervals of convergence. Maybe I should also very quickly do okay, it's a little tricky, but I could do a ratio test calculation for this. Hang with me here. Just take a minute here. The general term could be written like this. It's a little tricky, but you can write it like this. The fact that you have only odd powers means you need a 2k plus 1. There's your ak. If we look at the absolute value of ak plus 1 to the absolute value of ak, ultimately the negative ones go away. I think you get x to the 2k times the absolute value of x squared over 2k. I'm doing a calculation in my head here. 2k plus 3, I believe. Well, this might be a 3 here. think it's a 3. I think this is what you get. I'm not positive. I'm doing a calculation as quick as I can in my head. That cancels with this. This partially cancels with this to leave absolute value of x squared. I get 2k plus 1 times the absolute value of x squared over 2k plus 3. As k goes to infinity, that approaches the absolute value of x squared. And to be less than 1 is going to guarantee convergence from the ratio test. And that is equivalent to the absolute value of x itself being less than 1, effectively by taking the square root of both sides. And that's equivalent to x being between -1 and 1. So once again, the ratio test doesn't give you the full interval of convergence because it doesn't tell you anything at the right endpoint in this case. But we could use the alternating series test to verify it does converge at the right endpoint. Does it equal the arctangent function? It turns out to yes, but that takes extra proof.